Once again, you will often hear me call these the circular functions because they all go back to unit circle. Right, the coordinates on the unit circle are cosine theta, sine theta, and they're defined in terms of radian measure um, counterclockwise from the positive x-axis. So if you hear me say circular functions, I mean these guys. Okay. Welcome in, Gabby. Now, these are the new formulas we'll talk about. We'll go through the derivation of these today, and then these derivatives work just like the other ones, right? It's like the Pokemon trading card game. They come out with new cards. They work just good with all the other old cards. My wife's big into that game. She runs Pokemon tournaments and leagues and stuff in the area. So these are just some familiar functions. Here's their derivative properties. They work with product rules, quotient rules, everything else, just like you would expect. And so it's up to you how you want to handle this. If you want to make note cards and just every day quiz yourself, that's probably a good strategy. Or some people, they go on to I think Quizlet. I think people have these on Quizlet. You can do that. But as we start getting these formulas, I recommend just take a couple minutes every day and just go through them. Right. If you work enough homework problems, you'll just know these things naturally. You follow? But let's look at where a couple of these come from here. Let's start off with this one. The derivative of sine is cosine. So let's see why that's true. So we gotta, what's going on here with my pen? Maybe I need to just restart this. So the derivative of sine is cosine. So the way we're going to derive these formulas is we're going to go back to the limit definition of derivative. So if you recall, the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h, provided the limit exists. And every single one of these derivative limits, if you actually plug in h equals 0, in the numerator you get an f of x minus f of x, which is the denominator, you get a 0. So every single one of these is a 0 over 0. And once again, that's because geometrically, we're trying to find a slope. And if you try to find the slope with only one point, you're going to get 0 over 0. So in this particular case, for the derivative of sine, that's our function. So we need the limit as h goes to 0 of sine of x plus h minus sine of x over h. And then the challenge is to somehow rewrite this to resolve the 0 over 0. Okay. So we need to go back and we need to evoke a trig identity that you may or may not remember. It's the sum formula for sine. It turns out if you look at the sine of the sum of two things, it's the sine of the first term times the cosine of the second plus the cosine of the first term times the sine of the second. So at some point in your trigonometry or pre-calculus, you saw something like this. Hopefully you had some kind of story as to why it was true. We're not going to spend the time to review that story today, but we're just going to use this in our limit. Oops, minus sine x. So, this is what we plugged in for sine of x plus h. Now we got to think back to, seems like forever ago, but it was, I think, like literally 2 weeks ago. Anytime you've got an indeterminate form 0 over 0 involving trig functions, we had a couple basic trig limits that we could derive using the unit circle and the squeeze theorem. And so we had this one, which this one kind of came back a little bit on the take-home. What's this limit? As t goes to 0, what happens to sine t over t? That goes to what? That goes to 1. And limit as t goes to 0 of 1 minus cosine t over t. Do you remember where that goes? That goes to 0. So the challenge here is I've got this now broken up into factors with cosine h's and sine h's. H is the thing that's going to 0. So what I'm looking for here is I'm looking to get sine of h over h. Welcome in. Because I know that would go to 1, and I know this goes to 0. You follow? All right, so now I got to go in there and see if we can do some algebra to kind of get these things sorted out. So here, once again, the limit is on the h. So here's the h down here. And I'm looking for a term that's got a sine h in it, and sure enough, I see one. You follow? And then I'm looking for like a 1 minus a cosine h, and I am seeing that other stuff. So what we're going to do is we're going to just break up the numerator here. I'm going to write this term first, the cosine x sine h over h. Whoops. And then I've got the rest of this stuff. I've got a sine x cosine h minus sine x. So I know where this one is going. Right? As h goes to 0, I know this is going to go to 1, so that's dialed in. Here I got a little more work to do. What can I factor out of both of these terms? Oops. So what can I factor out of those two? Sine. And then what would be left in the numerator? What would I have left? Cosine h minus 1. Okay. Now if I go back and look at the limit I know about, sine h over h I know about 1 minus cosine h over h. You follow? So how could I turn this cosine h minus 1 into a 1 minus cosine h? What could I do? I could factor out a negative 1. So instead of factoring out like a plus sine x, I could factor out a minus sine x. And so that's what we'll do. So putting all this together, I've got the derivative of the sine of x equals the limit as h goes to 0 of cosine x times sine h over h minus sine x times 1 minus cosine h over h. And now I'm all set to use my limit properties. So now I could use the sum and difference rule to break this up. And now we're going to do something that sounds a little weird, but the limit is on the variable h. You follow? As far as h is concerned, x is just a what? It's just a constant. There's no limit on that. So what can I do with these cosine and sine? I can bring them out. And now we're all set. Because we know as h goes to 0, sine of h over h goes to 1. 1 minus cosine h over h goes to 0. So for my final answer, I take the derivative of sine. I get cosine times 1 minus sine times 0. And here we go. The derivative of sine is cosine. Okay. So you know sine and cosine are phase shifts of each other, but they're actually telling you the slopes. So they're more intimately related than you may have first thought. So let's fire up Desmos. Let's look at the sine. And I'm going to put in some tangent line here. So I'm going to put the f prime of a times x minus a plus f of a. We'll add slider a. And we'll add the point a comma f of a. So we got the point of tangency. So you know, here's the tangent line as you move along the sine. You follow? Now let's fire up cosine. And we'll make that blue as well. So what this says is that the y values on the cosine curve match the slopes on the sine wave. So in other words, the y values on the blue curve match the slopes of the line on the red curve. You follow? So let's see if that works. As we move this around, for example, here you've got a positive slope that matches the y value there on that wave. You follow? So let's look as we move through here. Let's see what happens. Let's zoom in a little bit so we can see this. So as we scooch through here, as we move through here, and here's just to make it even better, let's put a comma g of a on there. So make this blue. Oops, whoops. Make this blue. All right. So the slope of this line should match the y value here. So check it out. So look what's happening. As we get near that maximum point, the slope is leveling off and it's going to what? 0. And then it starts to what? You see the connection there between the slope? Now the slope is negative, but it's getting shallower, right? So it's getting less negative, and then at the bottom here, it's going to go to what? 0. So then it goes to 0, and then the slopes are positive. So you see the connection between the y value on the cosine and the slope on the other one. So it works. Okay. Now you can go through a similar argument and derive the derivative of the cosine of x is none other than minus the sine of x. And you can play around and look at that graphically as well. So these are sort of the two big derivative formulas for the trig functions. And from these two, we can get the derivatives for everyone else. Because if you remember back from trigonometry, or if not, you've got that handout from the first day of class, you can express secant, cosecant, tangent, and cotangent all in terms of sine and cosine. And we can use the properties that we learned last week to help us figure out the derivative, say, of, let's do tangent. Let's say, what's the derivative of tangent of x? We want to find out what that is so we know it. But when we first get into it, I don't know. But we do know that we can rewrite tangent as what? Sine of x over cosine of x. And so we've created a fraction, which means what rule do we have to apply? Quotient rule. All right, so how's quotient rule go? Low d high minus high d low, and then you square the denominator, and off you go. All right, what's the derivative of sine? Cosine. Minus sine, and what's the derivative of cosine? We didn't go through the derivation, but you're just going to need to remember the derivative of cosine is negative sine. Yeah. All divided by cosine squared. So is everybody okay with the quotient rule, filling in the formulas? All right, cosine times cosine is what? Cosine squared. Once again, don't forget this negative. It's minus sine times minus sine. So this is going to turn into a what, folks? Positive sine squared. Good. Over cosine squared x. And hopefully this triggers a memory for you. I've got cosine squared of an angle plus sine squared of the same angle. That's always equal to what? Cosine squared of an angle plus sine squared of an angle is always 1. That's your Pythagorean identity there. But we can actually simplify this a little bit further using some definitions and some basic identities. What's 1 over cosine? Do you remember? That's secant. So 1 over cosine squared would be what? Secant squared. There we go. So once again, this would be a formula that you put on the flashcard. This is one of the basic formulas that you should know. Now, you can go through a very similar argument to get that the derivative of cotangent is minus cosecant squared. Okay? So derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of tangent is secant squared. Derivative of cotangent is minus cosecant squared. Are you picking up on a little pattern here? The cofunctions work like the regular ones do, quote unquote, except they pick up a negative sign. Right? And if I remember, we'll revisit this later in the week, which might be as early as tomorrow. It's summer. But there's also a reason for this that gets into what it means to be a cofunction. Does anyone know why cofunctions are called cofunctions? Like, where's the co come from? It comes from complementary angles. So we'll talk about that if I remember, which I probably will. Okay. Now, let's say you want to take the derivative of secant of x. Right? That's one of the basic 6 formulas. I'd like to know what it is. Good thing I can rewrite secant as what? Secant is 1 over cosine. And even though we're going to learn a rule tomorrow, that is a better way to approach these kinds of problems. At this point, we're stuck using what rule? Quotient rule. So we'll do low, high. Low D high. Minus high D low. And then you square the bottom, and off you go. All right, what's the derivative of 1? 0. So this first term just does what? And what's the derivative of sine? We just learned that one. That's what? Cosine. So it'll be a minus cosine here. Low D high minus high D low. Oh my goodness. Low isn't, what is this? I got ahead of myself. There we go. Now it's better. The derivative of cosine minus sine, but there's a minus out front, so it's what? Sine x. Okay. I got ahead of myself there. Okay, so the derivative of secant of x is sine of x over cosine squared of x, which I suppose is a fine formula, but typically we rewrite this. We write the denominator cosine squared as cosine times cosine. What's 1 over cosine? That's secant. And what's sine over cosine? Tangent. So that's the derivative of secant x. Okay. So hopefully this has been a trend you see all throughout trigonometry. If you know what's happening with sine and cosine, you know what's happening for the other 4. And the same is true in calculus. So once again, this would be a formula you put on a flashcard or whatever, on a Quizlet, whatever you want to do. You want to practice it every day. Now, anyone want to guess the derivative of cosecant of x? Well, it's a cofunction, so we're going to have the cofunction pattern, but instead of secant, it'll be cosecant. Instead of tangent, it'll be cotangent, and because it's a cofunction, the derivative is going to have a negative. Make sense or not, folks? Okay. So here you are. Okay. On the surface, there are 6 different formulas to know. You follow? But if you see the pattern, there's only what? Really only 3. Okay. So you want to practice these. The best way to practice these formulas is to work through them on these examples. So these are all videos. I would encourage you to try these problems without the video. Check the answer. If you don't have the right answer or you just have no idea where to start, then you can fire up the video and just scroll through it, things like that. Okay. But if you look, these are just functions that have these new basic rules along with old familiar friends like constant multiple rule, product rule, quotient rule. Number three, you go through the quotient rule and you end up doing a little bit of simplification. Okay, so number 3, you might get an answer that doesn't match the answer there. You can check your answer on Desmos to make sure that you're correct, and then think about how you can simplify. The thing about the sines and cosines, once again, you have all these identities, like sine squared plus cosine squared is always 1. Those are types of things that you want to take advantage of simplifying the derivative. Because what's going to happen in the not-so-distant future, aka next week, is we'll be taking these derivatives and having to do solving equations with them. So you're going to want to get it as simplified as possible. So, just keep that in mind. And then, some more here. Tangent line, things like that. Okay. So let's take a couple minutes and look at this exploration because this kind of foreshadows some deeper connections between sine and cosine and other things in the mathematical universe. Basically, it says, let's just start with sine and let's just start taking derivatives. All right. So I start off, f of x is sine, the derivative of sine is cosine. So that's we learned that 25 minutes ago. The derivative of cosine is not quite sine, it's what? Minus sine, because we got that cofunction there, so it picks up a negative. Now, if you want the derivative of negative sine, the negative, that's really a negative what? Negative 1 factor. Pull that out. Derivative of sine is, once again, cosine, so that would be negative cosine. And to your surprise and or delight, what happens if you take the derivative one more time? You get back to sine again. You with me or not? So now we're back to take the fifth derivative. It's the same as taking the what? So what's going to happen here? Yeah. These derivatives repeat in a cycle of what? 4. Exactly 4. So for example, if you wanted to take the 21st derivative of sine x, that would be the same as the what derivative? It would be the same as the first, right? You with me or not? You take 4 into 21 goes how many times? With the remainder of 1. You with me or not? It's every 4. Now, can you think back in the recesses of your algebra knowledge? Can you think of something else that repeated in a cycle of 4? It wasn't even in trig class. It was something in algebra. Do you remember this character? So you could start taking powers of I. Those things cycled around too in 4. Could there be some deep and magical connection between the derivatives of sine and cosine and the powers of I? Oh, there could be, and there is. And that's what we'll discover in Calc 2. So if you take Calc 2, keep an eye out for that. It depends on who you have for that, to be honest. I make a big deal of it because I think it's cool. Okay, there's that. And then there's your homework to reinforce what you do. Okay, so once again, when you sit down to review what we did today, look at the notes, make sure you follow them, and then dig in, work on those examples. If you get, check your answers. If you get stuck, you got the video to help, and then you got the homework for all kinds of extra prep.